Now it is my great honor to introduce Professor Jacques Bergmann. Professor Bergmann is Professor of Gastroenterology and Head of the Endoscopy Department of the Academic Medical Center in Amsterdam. And we are looking forward also for an AI system in the Barretts. And we will ask him, Jacques, do you think the computer can take it over for the detection with our problems?
Yes. Absolutely, maybe not on the day of today, but in the not too far distant future, I'm convinced that a computer will do a better detection job in Barrett's than the average endoscopist can. Mm-hmm.
So good afternoon, and welcome to my lecture on machine learning in endoscopy. Thank you so much for inviting me to this great Endo-Swiss endoscopy course. Me and my team in Amsterdam, together with our collaborators in Eindhoven, have an interest in machine learning, but mainly have an interest in machine learning for the use of detection of early Barrett's neoplasia. So here's 3 examples of early Barrett's cancers. And here is where a computer-assisted detection algorithm or a CAT algorithm may help you during your endoscopy. To build such a CAT algorithm, there's actually 2 ways to do that. The more conventional way is to tell the computer from a clinically inspired background what are the key features the computer should be looking at. So the human input of features of interest is what defines a clinically inspired approach, in which we take a good quality image of an early Barrett's cancer like this, cut it in small blocks, and then extract from each block the color and the texture. Now, if we want to quantify texture, we need certain algorithms for that, but that's something that modeling for people with the background of our technical university in Eindhoven is pretty straightforward. So a block would then generate numbers on color and color variance, and numbers on texture and texture variance. And then the only thing we need to do is then to tell the algorithm which blocks are neoplastic and which blocks are normal. And we do that by having experts delineate images like this. The computer will then depict texture and color in graphs, and we'll find a distinction line between the color and the texture of early cancers and the color and texture of normal areas. And using this dividing line, we can then make predictions about a new image patch. An image with this type of texture and this type of color would then be classified as an early cancer. This would then be a new image on which the algorithm would take all of these blocks, tell us which of these blocks are normal and which of these blocks are likely to be neoplastic, and then post-process this into a delineation, as you can see on the right-hand image. Now, using this clinically inspired approach, we have created an algorithm that actually works pretty well. On the right-hand side of each of these pairs, you can see the delineations by 6 experts, and here are the corresponding delineations generated by the algorithm. A very subtle lesion here recognized by the algorithm and beautifully delineated. Same here if you relate that to the 6 experts. Now, the downside of a clinically inspired algorithm is that the algorithm can never be better than your human input. And most machine learning approaches nowadays are moving away from this clinically inspired approach and are using a deep learning approach, in which the algorithm learns from the data itself without us telling that texture and color are the only determinants. Generally, this is a 2-step approach in which we use large available data sets like ImageNet, which contain millions and millions of images, all labeled as cats and dogs and houses. There's 30 categories of cars and dogs in there, enormous amount of information. And the algorithm uses that information to learn basic features of images, like boundaries, like edges, like shapes, etc. And superimposed on that information, so after this pre-learning, we then do specific training for which we use specific images. In this case, early neoplasia images of breast cancer that we don't have millions and millions of, especially not since we would also need to have them be delineated by experts. So this ImageNet dataset is the dataset that is used by most machine learning algorithms in endoscopy. It now contains over 40 million of images in over 20,000 categories, and these are all hand annotated. And a significant number of those not only have the annotation telling you that this is an image of a bird and a frog, but it also will have boundary box telling you where the bird is and where the frog is in this image. Segmental information. So this uses the optimal setup to keep your precious data for specific training and do pre-training on largely publicly available data sets. Now, one of the dangers with this approach is that if you want to detect early neoplasia, you still need to feed the algorithm with enough information on early neoplasia, especially since the distinction between normal and neoplastic is sometimes so subtle. So circling around in a data set that is too small is one of the biggest mistakes for poor quality CAT algorithms in endoscopy. Generally, what you do if you want to make optimal use of your data set is that you train and validate your algorithm on the same set. You use a trick that's called internal cross-validation, in which you train your data set on usually 80% of your data and then validate it on 20% of the data. And you can do this 4 times so that you move the training set and the validation set through your available data set. Now, the advantage of that is that you're using all data for both training and for testing. And you therefore make optimal use of your precious data. The danger is that you run the risk of overfitting. If your data set is small, and if you only have a single data set, and especially if you do too much of this cross-validation, I showed you an example of 4-fold cross-validation, which is pretty okay, but if you would do a 20-fold cross-validation, you will be circling around in your database too much. And basically you would find the optimal distinction line, but not from early Barrett's neoplasia in general, but only of your data set of a limited number of early Barrett's cancer. You will be modeling the noise as well as the relevant information. So key elements of good quality CAT studies is that they need to have an external test set, a test set that you have taken somewhere else that you've not used for training at all, that comes from another hospital or preferably multiple other hospitals, and that you then use that test set to see how your algorithm is performing. And logically, that external test set should have true challenges for endoscopic detection. It makes no point to look at a test set with huge polyps or with huge Barrett's cancers. Here, you don't need a CAT detection tool. So a performance score of a CAT algorithm only bears relevance if you know how well endoscopists would have done without the CAT algorithm. You need some kind of reference. So this is what we've done in our Barrett's deep learning algorithm. We've done a couple of things differently than what I've shown you thus far. First of all, we did not use ImageNet, but we used a large data set only of endoscopy images. So our algorithm learned the basic features of endoscopic images from endoscopic images, instead of learning basic features of endoscopic images from images of cats and dogs and boats and houses. Made more sense to us. Secondly, we had 2 quite big data sets, 1,200 images of cancer and non-dysplastic Barrett's in a 50-50% split, and a second high-quality image set of 300 images, all obtained with high-quality Fujifilm equipment. We only use that for pre-training, training, and the internal cross-validation that I showed you on my previous slide. And then we took this and tested it on not one, but 2 external validation sets. Each of these 2 sets coming from different hospitals. And all of them contained images that were really very subtle, as you can see on the right-hand side on this slide. So we had images like this with an early cancer and here with an early cancer. Here is then what the algorithm did to predict its performance. This is how a delineation and a biopsy spot would look like. And this is what the experts made of these images. If we looked at the performance of only the internal validation, and sensitivity probably being the most important test characteristic, 88% sensitivity was pretty much okay. But it doesn't tell you a thing because it can be overfitting. So this is why we had 2 external data sets. And to our relief, the sensitivity actually was even higher in these 2 external sets. The 5th data set that contained these subtle images, we were very pleased with the 93% sensitivity. But then we did not know how endoscopists would do. So what we did is that we had these 80 images be assessed on a web-based module by 53 general endoscopists. And what we found was that these 53 endoscopists had an average sensitivity of only 72%, whereas the algorithm clearly outperformed these endoscopists. And if we look at this ROC plot, in which we project sensitivity on the vertical axis and 1 minus the specificity on the horizontal axis, the algorithm is here. And here's the performance of the 53 endoscopists. The closer you are to this spot, which is the perfect test, the better your performance is. And you can clearly see that the algorithm outperformed all 53 endoscopists. So machine learning and endoscopy for sure is here to stay. My lecture was focused on having machine learning help you in the endoscopic detection of what can be seen, but what is not necessarily recognized by every endoscopist. So subtle early Barrett's cancers, early gastric cancers against the background of atrophic gastritis, or sessile serrated adenomas. We will also likely use algorithms that help us to make decisions during the endoscopy. So some of the lesions it will detect, you may not need to biopsy because an algorithm will say you this is not dysplastic. Or it may tell you it's cancer, but it's likely to invade in the submucosa. Do not resect this. This patient needs to go to surgery. Detection and characterization, logical things that endoscopists struggle with. But I think the biggest impact will likely come from algorithms that will help us to improve our endoscopic quality. Algorithms that will tell you you're pulling back too quickly, or you've fallen back behind a bend in this colon and you need to go back. Or this part of the gastric stomach you have not yet investigated. Detection and characterization algorithms can only work on images we supply, and it can never be better than what we supply them. Quality improving algorithms will help us to expand on the information and will unfold blind spots and also will unfold poor performing endoscopists. The downside of machine learning endoscopy is that it will likely increase disease burden. The current colonoscopy detection algorithms lead to an enormous overdiagnosis of small sessile serrated polyps and small hyperplastic polyps that really bear no clinical relevance. So here we will struggle with, and we might have difficulty in how do we distinguish irrelevant findings from relevant findings in the near future. Nevertheless, machine learning is an exciting field. If you want to learn a little bit more about the basics, this is a good paper that we published in God. It's entitled Practical Lessons for Endoscopists. It's an easy read. And if you're interested in this field, and if you're an endoscopist, I would strongly encourage you to download this paper from God. Thank you very much for your attention.
Thank you, Jacques, for this wonderful presentation. I think it shows your outstanding scientific work in this field. My question to you is, which light do you use for the collection of the images? Is it still the white light, or do you use NBI images or maybe TXI images? How do you approach this?
Yeah, it's a good question. We might be tempted to build algorithms for each of these different imaging modalities. From a computer algorithm perspective, white light and TXI is actually not that different. And a lot of the training work that we actually do with these white light images is to distort these images, to reduce or to increase contrast, to turn them around and to modify them. And all this downgrading and upgrading then leads to supplying the algorithm with different background types of white light imaging. And basically TXI is exactly that, a post-processing on a white light image. So although we've not been able to demonstrate that since we're still collecting imagery on this, my take on this is that I expect that if we build an algorithm that works on white light imaging, is very likely to have a same performance on TXI. But that's one of the things that we're working on, and we're looking at results probably by the end of this year to make sure that actually that we're on the right track with that.
I think it is also very important how you collect these images. Must be also a good performance of the endoscopy, how you collect the images. And the second point is what I was thinking, from where do you get all these images?
Well, that's a good point. In the work that I've shown you, a lot of this actually came largely from my own unit, and a significant part of that was retrospectively collected. That may be good from a homogeneity perspective, but it actually reduces the robustness of the algorithm that you're building. So ideally, you want to have a very heterogeneous data set coming from multiple centers, from multiple endoscopists, with multiple types of endoscopes, with multiple ways of actually storing and compressing the files, etc. If you have a very heterogeneous data set, which then still should be big enough, and you create an algorithm based on that, that algorithm will have not only better performance, but also a better robustness. So it will be better proof to deal with the variability between centers and between the different setups that they will have for their endoscopy system. Big issue here is also that if you, especially for Barrett's imagery that you collect, if you use only retrospective imagery, basically every image that you have on an early cancer is an image of a lesion that has been detected. The endoscopist finds it and then takes a picture, and that's then in your retrospective data set. In the practical application, you want the algorithm to detect the lesion the endoscopist is not seeing. That endoscope position then is different. So that means that for building a good algorithm, or at least testing a good algorithm, you should supply the algorithm with a neutral endoscope position, which is basically the same if you're looking at a non-dysplastic Barrett segment or with a Barrett segment containing a lesion. So this is where we're now running a large-scale project, and Zurich is one of the lead centers participating in this, in which we very rigorously collect prospective imagery, try to avoid that hidden bias that is a threat for all machine learning projects in endoscopy, trying to eliminate that as good as possible.
Thank you. I think Michael has a question as well.
Yes, I do have. So, Jacques, I have a more clinically oriented question. So I think that we as endoscopists, we don't really like a Seattle protocol. So I remember when NBI was on the market, everybody expected, oh, maybe it will replace the Seattle protocol. So what are your feelings about AI and potential replacement of Seattle protocol?
There will be no way to escape on some kind of tissue sampling, because the majority of patients that we will do endoscopies in will not have any neoplasia or dysplasia. And so the algorithm will say there's nothing there. And then there will be very little that is then missed. And still we need to predict which of those patients is going to progress and who we can leave alone or at least prolong the surveillance interval. My take on this is that we will use CAT to find any subtle visible lesion that's there. And if there's nothing there, we will likely brush the Barrett segment and then look for markers that predict what is missed, which will be very small, but more importantly, which patients will progress. Those we will probably ablate, and all the other patients we will leave alone. And the first step is to do those brushings transendoscopically, but within 10 years' time, we will probably do all these brushes transorally, so without an endoscope, probably at the general practitioner's house, and only send those patients with an abnormal cytology brush or cytology sponge, who will then likely need treatment instead of imaging and boring Seattle biopsy protocols.
Thanks so much.
Ambitious future, I must admit.
Thank you, Jacques, for this interesting future perspectives. And I pass now to Michael for the next topic.